All right, it's 9 o'clock. Let's get this rolling again. So, good morning, everyone, or whatever time of day it is where you are. Thanks for joining me again here on day 3. Today's focus, as promised, will be on autonomy, or perhaps more accurately, how Goby3 connects to and provides support for existing autonomy systems and new ones. So before we get started, just want to remind people that, again, we'll have a homework following this lecture. And if you have questions on that or any of the previous days' homework, please feel free to join in on the office hours, which will be 1 to 3 and 7 to 9 in the afternoon, evening, my time. And I'll post that again on Slack, the links for that. Also should mention that I pushed my solutions to the homework from yesterday into a branch called Post Homework 2 on the GitHub repository for Goby3 course. So if you want to take a look through those, if you want to compare how I solve the problems or whatnot, feel free to do that. And if you have any questions about what I did, again, drop into Zoom for the office hours and I'll give you a hand. Okay, so now switching over to today's lecture. Again, this will be recorded and posted online, and publicly available. So keep that in mind. So Goby is primarily a communications project in some sense, but really we want to be able to build autonomous systems with it. And so that requires a bit more than just communications, obviously. And so today we're going to look at this sort of second point of the triad that I showed on the first day. So as you recall, I had this slide on the first day where we looked at communications yesterday, look at autonomy today, and sensing tomorrow. And so the first thing that we have in Goby for sort of linking us to autonomy is on the vehicle control side of things. So we've adopted this abstraction from Moose IVP, which is this front seat, back seat concept. And basically you have a front seat driver as this vehicle computer, like the manufacturer's computer, which is generally tuned for a specific platform's control paradigm and design. And then the payload computer, which is referred to as the backseat driver because it's telling the front seat what to do. So that's Moose IVP, Goby, etc. And so the reason this abstraction is useful because it allows us to deploy our autonomy software on a wide number of different vehicles, different manufacturers, without necessarily worrying about the specifics of the control of each of these vehicles. So we're going to look at some of the tools in Goby that allow us to carry out this abstraction. And that main tool is the Goby front seat interface, this application. And so what do I mean by a front seat interface? Basically, it's got several main functions that it's going to carry out. It's going to keep track of the operational state of both the back seat and the front seat. We'll look at that in a second. And it's going to forward commands to the front seat. So desired set points, which are often heading speed, in the case of underwater vehicle depth. And these set points are usually sent at about a hertz, slower than the control loop. And then it's up to the front seat control system to figure out how to actually execute those set points in some reasonable amount of time. And intentionally, that's not highly constrained because that lets us work with a lot of different platforms. So then the other two pieces of the interface is to send and receive data, which is sort of generic, but this could be sensors residing on the front seat that the payload needs to know about, navigation solution. Much of the time, the front seat is running some sort of navigation estimation, which the payload definitely wants to know where the vehicle thinks it is. And the other would be to send data to the front seat for any sensors that reside on the payload that the front seat needs to either carry out its computations or to log or whatever. So this can be depending a little bit vehicle specific. So looking at this sort of the states of both the back seat or helm and the front seat as they're seen by Goby front seat interface, they're very simple state machines. Is basically either the helm, which is what the kind of the captain is either in drive, in other words, it's producing a desired set of set points, like heading speed depth, or it's in park, which case it isn't. And then the front seat state is, this needs to be sort of inferred by each driver, which we'll get to in a minute, what the front seat is doing. And it's also intentionally quite simple. It's either an idle, which is sort of powered on, but not in a mission. It's in a front seat mission, which means that the vehicle is under the control of the front seat computer, in other words, the manufacturer computer. And the payload might be listening for data at that time, but it's not in control. And then accepting commands is when the front seat is accepting payload set point commands. And so given these two state machines, we basically end up inferring the state of the overall interface, which is this third state machine. And so this one's a little bit more complicated, but when it starts up in idle, reads the configuration from either command line or the configuration file, it goes into standby. And then once the front seat provides some amount of data to the payload, meaning it's connected and streaming something, usually navigation data, but could be a heartbeat or something else. It goes into listen mode, at which point you could run an entire mission under front seat control while the payload's in listen. So that's why this is part of the parent state running. And if we enable the accepting of commands, which is going to be very vehicle specific how this is done, then the interface goes into command mode, assuming also that the helm is in drive. So if the helm's in drive and the front seat's accepting commands, the interface is in command mode, and that's when it starts streaming desired set point commands over to the front seat computer. And this is sort of the, I guess, nominal operation state for a front seat, back seat payload system. And the final two states are a variety of helm or front seat errors, depending on who threw an error. Keep track of those in there. So this is a revisit also of a similar slide I showed on Monday. And here we're looking at the publish subscribe interface for Goby front seat in a graphical manner. So Goby front seat is primarily one thread. There's a second thread I'll talk about we can optionally use in a bit. But the main subscriptions are this command request. So this is where those desired set points come in from the helm, like heading speed depth. And the main publication is this node status, which is going to be given the vehicle's estimated position and navigation data. You know, that is used by a lot of the payload systems to know where the vehicle believes that it is, its depth, its pose, like pitch, heading, roll, things like that. And the other publication that can be useful is a status, which gives a summary of those states, what are these three state machines, what states they're in. So that's that status publication. And we'll look at all these in a minute, but those are the main three that I would say to focus on. And so then how do we add vehicles to this? It's implemented as a C++ library plugin, if you will, that's DL opened and run at runtime. So you can add your own vehicle support to this inside of Goby or as an external library that you load at runtime. And the four that are provided inside of Goby and the open source distribution at the moment, there's one, the basic simulator plugin that connects to this fake simulated vehicle. That's what you've been working with in the homework. There's a plugin for the General Dynamics Bluefin vehicles, their standard payload interface. There's one for the SV2 series of wave gliders, so liquid robotics wave gliders. And there's one for the Ocean Server or L3 IVR vehicles. And so as I mentioned, the second thread here, down here, this front seat translation is ultimately how we connect to Moose. But we'll look at that quite a bit more in detail. So no point to belabor it now. All right, so we're going to switch off the slides now and get back into the code. So So the first thing I'm going to do is launch or rather change the warp speed of the simulation so that it's warp 1, in other words, running at real time, so that things are a little bit more reasonable pace to look at. So I can do that either by running this generate all launch script with it needs 0 vehicles at warp 1, and that just really just sets this config common sim.py setting warp equals 1. So I could have set it in here directly as well. But we have this convenient script, might as well use it. So then I'm going to launch the mission here. All.launch, which just runs the USV and the top side at this point, because we're going to look at the USV's interface. So if I open liaison on the USV, which is 50,001, this is Goby liaison running on the USV, and then I go into the scope over here. I see all the messages being published currently on the interprocess layer on the USV, and I can filter these down. So I just want the ones that are related to the front seat interface, which all have the sort of namespace of front seat. So I can filter this display on the front seat interfaces using a regular expression. So we have those. Split this over here so you can still see the whiteboard. Put this over here. Okay, so there's a fair number of messages that are being published in this front seat set of groups. So let's look at them one at a time. So the first one here, we've got this data from front seat, and this message is all the data coming from the front seat, not surprisingly. So this is data from the front seat to the payload or back seat. And generally, this includes, at a minimum, this is going to include this node status subfield. And that includes things like the type of the vehicle, the latitude, longitude, depth. In the case of this is a surface vehicle we're looking at, so depth is 0. An X and Y local fix, which is based on a UTM grid with a local coordinate origin that we define. The heading and pitch and roll in the case of a non-simulated vehicle. This basic simulator doesn't simulate pitch and roll. And then the speed. So this data from front seat can also include, instead of a node status, it can include other vehicle specific data. It could be things like sensors connected, like raw sensor feeds, whatever your vehicle needs to send from the front seat computer to the payload. So then the second message in the list here, we've got the desired course, and this is, as the name suggests, the desired heading and speed in the case of a surface vehicle, and then also depth. Could also include other things like pitch and roll if you can control those separately, depending on your vehicle's dynamics. So at a minimum, this is usually desired heading. In the case of like the Liquid Robotics Wave Glider, that's all we can send because you can't even control the speed of that vehicle. But the sort of 3 of heading, speed, depth is pretty common pairing to use. And then we've got the helm state, which is the either drive or park, as we saw in a minute ago in the figure. Then we've got node status here, which is a convenience breakout. This is really just convenience republish of the node status field in data from front seat. So data from front seat can include things other than node status, and sometimes if it doesn't even include a node status. So this is just a republish because it's such a common use. So many of the applications want to know this that it's just republished on this variable alone. And then we've got the raw in, raw out publications. And this is basically the raw stream to and from the front seat. So this depends a lot on what the vehicle's payload interface looks like, but this could be something like Enemy 0183. In case of like the bluefin vehicle, it could be some kind of binary protocol. In the case of the wave glider, it could be some kind of, I don't know, I'm going to call the Ivor one Enemy 0183 but it's not really. It's kind of like that, and then they hacked it. So some kind of whatever the actual data being sent to and from the driver and the front seat looks like. And so in the case of this simulator, I've made up this fake protocol that we'll look at more later, where the navigation messages are just strings prefixed by nav, and the commands, the set point commands, are just prefixed by CMD, and they're ASCII based messages. So the last message we see here is the status, and this is the states of the sort of three subsystems, which are the interface, which is Goby front seat interface's state, which is in command mode right now. And that was the graphs I showed you earlier. Front seat state, which is accepting commands, and the helm, which is in drive. So that's showing us the three states that we saw here. This is helm and drive, front seat accepting commands, and the interface in command mode. So as I said, that's kind of the nominal operating state for us. Okay, so once we've looked at that, if we look at the full publish subscribe API for Goby front seat interface, there's a few more things. And as you recall from previous days, if we go into share Goby interfaces, within here, there's all of the interface files that are generated by Goby Clang tool, which I alluded to in the first day, and we'll look at more at the end of the lecture. But the one for the Goby front seat interface is this one. So if we look at that, YAML file, we see the full publish subscribe interface. So the interprocess layer publishes all these messages, and we've looked at most of these. So we've got the data from front seat, node status, raw in, raw out status. We looked at most of these. There's a couple that we haven't. It also publishes a command response that we didn't see. And this is done, so the command request, which is the pairing of this, can be sent from the payload, and that's actually generated also from the desired course command. So the desired course is a single option, essentially, for commands. It's the most common one. But you could also have commands like enable lights on the vehicle, or enable a buoyancy engine, or whatever your vehicle can support. You can add commands to the driver that support those extra features. And some of those commands you want to have acknowledged. So maybe I want to tell the vehicle to turn on its recovery light, and I want to know that that's been done. So the command request would have turn on the lights, ACK requested, and then when the vehicle's front seat acknowledges that, you'll get a command response saying the lights are on, essentially. So that is done. We don't acknowledge the desired course commands, at least in this simulated driver, mostly because if you miss one, you just want to send the next one. You don't care about the fact that you missed one as much as you want to just keep sending the newest. And the other message that we haven't seen, or we're not seeing in the simulator right now, is down here. The payload interface subscribes to this raw send request message, and that's used for if you wanted to essentially bypass the driver and publish data straight to the front seat from one of the other processes on the vehicle, you could use that. And this is used for if you want to develop a new feature against the vehicle but not modify the driver, you can test it out by using the raw send request and then subscribing to the raw in, so you can see what it responds with. Add your new feature outside of the driver, and then ideally you'd also eventually update the Goby driver or write a new one to include that in the driver, but kind of a backdoor that can be handy for certain debug scenarios in certain new development situations. So now that we've kind of looked at the innards of the publish subscribe for Goby front seat interface, API. We have the basic simulator driver. Let's take a look at that one, because that's the one you've been using this week. And it's also probably the simplest one. Okay, so each driver that you write is going to be an implementation of a single class, and that base class is interface base, or in the full namespace qualified form, Goby middleware front seat interface base. And we're going to look at this. You could open up the header file for this, but I want to keep showing you different ways you can look at the documentation for Goby. So if you go to goby.software, you get the Doxygen generated documentation for the project. And if I look for interface base in here, I can click on that and find the full interface for that class. And so each driver has got to implement six pure virtual methods. So and these are shown here. We've got send command to front seat, send data to front seat, send raw to front seat, provide the front seat state, is front seat providing data, and then this loop method. And so the first one of these is send command to front seat. And this, as it suggests, is called by the underlying implementation or the underlying interface base when there's a command to send. So and this is often our desired course. So heading speed, depth, that kind of thing. And it's up to the implementation to take that command, convert it into whatever format the payload interface requires, and then send those messages related to that. The next one is going to be send data to front seat. And again, this is pretty much obvious from the name, but this is any sort of data that needs to be sent from the payload to the front seat. And then this could be nothing, and it's often nothing. This would only be if you had your payload that had certain sensors that connected to the payload that are needed by the front seat. And an example of this might be if your payload had, say, a USB-L receiver, and you had a capability to send those messages to the front seat to improve its navigation algorithm. You could feed that stream through there. Then we have the send raw to front seat, and this is for the backdoor feature to send raw messages from other processes, and that's using the message that we looked at, the subscription that we looked at earlier, the raw send request subscription, is what triggers this. So then the next two are front seat state. So whenever this is called, the driver must provide its understanding of the front seat state. So this is going to be based off of messages sent between the driver and the front seat. And it could be explicit handshake, like the front seat says, you can take control now. and then you'd be in accepting commands, or it might be more implied. It depends on how well designed the payload interface is for the particular vehicle. And then we have front seat providing data. And this is sort of, is this true if the front seat is streaming normal data, whatever that means for a particular vehicle, but usually navigation, position, maybe a heartbeat. And this needs timeout if it isn't. So that also would be used to determine if the front seat has stopped responding. The driver is required to return false if there's a timeout on that. And I said 5 or 6, sort of counting loop as one of these or not. So loop is, this is very much analogous to the loop in the Goby applications. And this is called at 10 hertz in this particular application. So so we've got those. We also now have, besides these 6 virtual methods, the driver is also responsible for calling these 4 signals. So that's kind of how data goes back to the interface, the base class. So in response, the driver has to call 4 signals. And these signals are command response. So that one would be called, this is called when we get NAC from the front seat. So again, if I had sent, turn on my lights, and the vehicle's like, the lights are on, then the driver calls the signal, and that's goes out to the base class and ends up publishing the appropriate message on command response. And there's signal data from front seat. This is called when we get data from the front seat, and this is typically the kind of mood status nav data. Could also include other types of data depending on the vehicle. And then finally, these other 2 raw signal raw from to the front seat. And this is called with the raw message sent or received, I should say, and then sent by the driver. And this is useful for logging purposes. It's also useful for any, if you want to try to implement new features outside of the driver, it can be good to have. Okay, so now that we have the interface for writing this driver, we can actually start looking at the code for this basic simulator. So we have the basic simulator itself is a standalone application, Goby basic front seat simulator. Standalone, by that I mean it doesn't connect to the Goby3. And it implements this very basic dynamic simulator, as well as this made up API between the payload and the front seat. So the API looks like this. I'm going to copy it out of the documentation for it. But basically, we've got the front seat simulator runs a TCP server. All the messages are new line and carriage return new line limited. And then we've got this init message that we send from the simulator, or rather from the payload or a backseat that initializes the simulation at a particular location for a particular time, run at a particular control loop rate, and then the vehicle parameters, if you will, which are pretty minimal. We have an acceleration value we can set, a heading rate, and a dive rate, and finally the warp factor. So we can tell our simulator we're running it faster than real time. It has to map to the one we're running on the payload. So once we initialize the simulator, we can send, well, in response to that initialization, the simulator will say, okay, you're in control, which is the state payload message, which would be essentially accepting commands. And then if you have a duration for a timeout for your mission, after that timeout is up, the front seat will say idle. It's basically the mission has ended. If you set 0 here, which is what we're doing in this course, it never times out. Then navigation is sent from the simulator using this simple nav command, nav message. And then desired set points are set using this command message. And those commands can be acknowledged. Either they're okay or there's an error. So this is kind of, I mean, this is not terribly far from some of the interfaces, at least in concept. It's simplified quite a bit. And the ASCII syntax is perhaps a little easier to read than maybe a binary protocol would be that you'd have to implement depending on the interface. So we keep it simple, but it shows all the main ideas that you need to deal with when you write a real driver. So let's take a look now at the code for the implementation of the driver for this basic front seat simulator. So that's in SRC, or rather within the Goby project, Goby3 SRC middleware front seat simulator basic. And so we've got the main code are these H and CPP files. So we'll open up both of those, CPP and header. And at the same time, I'll ask you to keep an eye on this diagram here. So we're gonna, let's turn off the auto scroller. So the sequence diagram explains the whole set of messages going between the basic simulator front seat interface. So that's this implementation of interface base that we just looked at. The Goby basic front seat simulator. So that's the front seat in this context, the simulator for front seat, but that's the, that would be, in a real vehicle, this would be the front seat computer. And then interface base, the base class that is common for all of the drivers in Goby front seat interface. So, so following along kind of with the sequence diagram and the code in the constructor for the front seat simulator interface, we start up a TCP connection to the simulator. And once that's active, we're good to go. And essentially once we're going, we're in this loop method, there's a couple of things that the driver does. So the first is this check connection state. So that's down here. If the connection isn't active, it just spits out a warning to the glog. And if it is active, and the first time it switches to being active, because previously it was not connected, it will send the start command. So this is basically the first time it's connected. It switches the front seat state to assume to be idle now that it has a connection. Sends the start, which is what seeds all the simulator values. And you wouldn't necessarily see something like this in a real driver because you don't need to tell a real vehicle where it is. But you do need to do that for the simulator. So this is a little bit of a special case. Then so in this write function, which is down below here, this is used to send every raw message to the front seat. We also call signal raw to front seat, and that's where we send out that message back to the interface base so that it can be published for logging on the raw out group. And then so the other part of this is back in the loop method. Once we do check connection state, we do try receive. So here's where we receive all the data coming off of the front seat itself. So within here, we could potentially handle any type of message off the TCP socket. Ultimately, it calls this process receive function. And then looking at the various possible keys, there's the CTRL one, there's a nav one, and there's the CMD result message. And so we're expecting to see this control state go to payload. And that's when the front seat has told us we're in control. So if we get this payload message, we switch our front seat state to be front seat accepting commands. And that's essentially when the interface will start actually sending desired heading speed depth to us. So we go into this loop, this data command loop at that point, which will continue while the whole mission runs. And so every once in a while, I think it's every 10, as at 10 hertz, the front seat state's called by the interface base. We're saying, you know, is the front seat still in accepting commands, or is it changed? And so our driver is responsible for returning the known front seat state, which we store in this class variable front seat state. It also asks us, is the front seat providing data? And we determine that in this driver off of the nav message. So if we receive a nav message, we set front seat providing data true. We also set a time when we last received data from the front seat, so that back in the loop method, we can check a timeout. If we haven't received data from the front seat for some period of time, 10 seconds, I think in this case, we set front seat providing data to false. And then the interface will automatically go into an error state, at which point, you know, that's a sort of an existential question as to what to do, given that usually you can't recover the vehicle without the front seat working. But it's also why the front seat would have to implement some sort of recovery safeties of its own. Because the payload only has so much control in that situation. So the other thing that we're always receiving once we're in this data command loop, essentially, is this nav message. It should be streaming off of the front seat, and that's where we get the heading speed, depth, and position of the vehicle as estimated by the simulator in this case, or in a real vehicle, the navigation estimation algorithms on board. And then once we have that, we call signal data from front seat, which provides that status message out to everyone else. And so this will trigger a publication of both the data from front seat as well as the node status message. And the last piece of this is the send command to front seat. So these will be streamed from the helm ultimately, I guess, is what is generating those. And just figure out where that function is in this particular CPP. So here we go, send command to front seat. So the only command that the simulator driver supports is the desired course command, and it will heading speed and depth are the three domains it supports. So once it gets this command, it'll write that to the outgoing serial port to driver. That's this command here. And then if we set the ACK requested, which we don't in the simulator, we would get a result. But if we had other types of messages that we wanted an ACK for, we would get that result. And then again, every message in, we also call signal raw from the front seat, so that we can keep track of all the raw messages we received as well. And then optionally, if you had that sort of backdoor, if you wanted to use the backdoor, then you'd have the send raw to front seat message would be called, or rather method would be called, and then you would send your raw and get the result. So that's the full. So this is kind of the full minimal implementation of a driver. And then you can look at the ones for real vehicles. They're a little bit more complicated, but not much. Essentially the same thing, just with usually support for a few other types of commands potentially, and obviously a different message set. You know, this ASCII CMD nav is just made up. Okay, so now that we've got our driver, how do we actually run this? And so I'll look a little bit into that. So the actual binary or application is Goby front seat interface. But on its own, Goby front seat interface can't do anything. It's not, it won't run without a driver. So it must have a driver. Otherwise, like, what vehicle am I connected to? I don't know. So if I try to run it on its own, it just gives me this error that I have to define this environmental variable. And so you would set this environmental variable to the shared library that you build with your driver, so that it'll open that driver and use it to connect to whatever vehicle you have. All the ones in Goby have a wrapper that are handy. So there's, if you look at Goby front seat interface, there's a wrapper script for the basic simulator, the bluefin driver, the Iver driver, and the waveglider driver. And what these look like, if I just do if I just look at the contents of this script, nope, which, not the contents of that. So these wrapper scripts like underscore basic simulator are just setting the load library path to wherever I built the project, and then setting front seat driver library to, in this case, the basic simulator one, and calling exec on Goby front seat interface. So you can use these wrappers as if they are standalone applications, but what they really are Goby front seat interface loading a particular front seat driver library. And let me maybe make this a little bit more clear by a figure. So this is sort of the plugin model for Goby front seat interface. You have some code for your driver that you compile into a shared library, and that shared library must have an implementation of the front seat driver load function, which is a C function. And so then when you pass that to Goby front seat interface using this front seat driver library variable, it will open this library, call this function, and that loads up their driver. So it's a mix of compile time and runtime. And it's done this way so that you can write drivers for your vehicles using the open source project without having to share that code with the project. Though obviously it would be much appreciated if you do have drivers you can open source to contribute those back. Okay, so now we're going to switch gears a little bit to the other half of the equation. So we looked at how we connect Goby to the vehicle control system computer. Now we're going to look at how to connect Goby to external payload autonomy systems, in this case, Moose IVP. P-Helm IVP, for those of you who are not familiar with it, is a rather useful multi-objective behavior-based decision engine. So that's a bit of a mouthful. So let's look at that. We got a multi-objective behavior-based decision engine, and it's from the Moose IVP project, which is Mike Benjamin. And what the multi-objective is, that's just saying that it can provide us solutions over a variety of domains, which are often heading, speed, and depth, but don't have to be. That's just a sort of trio that's commonly used for underwater vehicles. And the behavior-based is there's a plugin API for writing new behaviors. So what is a behavior? That could be like waypoint, follow waypoints. You can have a behavior that's avoid collisions. You can have a behavior that's trail another vehicle. And two of these, the waypoints and trailing, are already shown in the example trail mission, and so forth. And you can, your own behavior, whatever you want the vehicle to do, you can write these plugins behaviors for Moose IVP. And the Helm, what the Helm does is take those behavior functions. So each behavior writes a function over all the domains it works on, and that can be nonlinear. It can be all kinds of weird shapes. Takes several behaviors and solves to a single point decision over the objectives. So like heading, speed, and depth at every iteration, typically 1 hertz. So pretty neat project, and it's pretty widely used in the marine autonomy world. But I guess as far as we're concerned, it's Moose connected. So in order to use it, we gotta it's a Moose application and pretty tightly tied to Moose. So in order for us to use it in Goby, we want to create some kind of bridge between Moose and Goby. And everything I'll talk about here could be analogously applied to ROS. People want to use that. And that's definitely something that's on my list of potential things to do. And if you're interested in working on that, let me know. I can point you in the right direction. But it's not something I've had enough of a need for to have written it already. So how we do this? In Goby, we've got these threads that you can write that are based around Goby Moose Translator. And so Goby Moose Translator is a class that's it's actually a type def for basic translator with the template parameter simple thread. So if you're using a different thread trio, simple thread is, as you may recall, the inter-vehicle, inter-process, inter-thread 3-layer hierarchy that we've been working with this week. But you could use the translator class with a different hierarchy if you wanted to. This one's pretty common, so we have this type def for it. So in short, it's really there's the Goby thread half of it, which is going to give you the inter-thread, inter-process comms, and then there's the Moose, the C Moose com client, which is the kind of Moose enterprise client. This is how you publish and subscribe to variables inside of Moose. So you're given this little two-headed beast. Graphically looks something like this. So if I render this out here, you end up with something like this. So you've got Goby Moose Gateway, which we'll look at in a minute, or another multi-threaded application. So somewhere that you can run your Goby Moose translator thread. So you have your translator thread here, and inside of there you've got your CMOOS com client, so the Moose side, and you've got a Goby simple thread. And what ties these two together is the code we're going to write, and that's the part that depends on what you're trying to pass between Moose and Goby. So then the Moose com client connects to Moose DB, and anything that's downstream of that can get the data like phom IVP, and then simple thread connects to GobyD, just like everything we've done yesterday. So you can also have, since each one of these translators is just a thread, you can have multiples of them. So if you want to segregate the purpose of your translations between two different purposes. So I came up here one where we've got like the front seat translator, which is the one we're going to look at in a minute, for connecting to the helm. And say you wanted to also write your own one for some sensor that's connected to Moose and call it Moose Sensors Translation, you can write that and run it as well. And we're just saying, hypothetically, there's some sensor over in Moose that you want to get the data into Goby. You could write your own translator thread and run both of these. Okay, so let's take a look then at the interface for the basic translator, which is, again, I'll show it to you over here in the Doxygen documentation. So if we look at the protected member functions for translators, so the ones that are accessible to all the derived classes or our implementations here, we have a method called Goby that returns the underlying thread, which in this case for us is simple thread. And we have Moose, which returns this Moose interface thing we'll look at a bit. And then just the name of the translator and a loop method. So this looks a lot like loop in every other context that we've seen it so far. So really, there's just two things that we care too much about. You want to do something with Goby, you call Goby, and you want to do something with Moose, you call Moose. So that's pretty straightforward. What might be not as familiar as this Moose interface class is not quite yet Moose stuff for those of you who are used to Moose. It's got a few other helper functions to make connecting and using Moose a little easier. Within there, you've got comms, which actually gives you a reference to CMOOS comms client, so that's a Moose thing. But then we also have this add trigger method, which allows us to essentially subscribe to a Moose variable, and then when we get it, call this callback function. So this allows us to subscribe to Moose variables very much like we subscribe to Goby stuff. When we get the message, we get a callback. The other piece is this add buffer. So there's some Moose variables I might just want to have the latest value of for access later. So I can call this, and when I subscribe with add buffer, it doesn't have a callback. It just, every time it receives that variable, adds it to the buffer, and that buffer is accessible with this buffer method. So let's see this in action then. So we're going to take a look at the front seat translator thread, which is the one that connects this is the implementation of basic translator for p-Helm IVP, basically the desired set points and the navigation data back to p-Helm IVP so that the Helm knows where the vehicle thinks it is. And that should look like this. So this is pretty similar to what I showed you before, but now we've got this front seat translation is the class we're looking at, the thread we're looking at, and you've got the Moose Goby side here, sort of one foot in each world. You have the Goby side where the front seat interface that we spent the first part of today's lecture looking at. And then on the Moose side, you've got two applications that are responsible for dealing with the data that's received here. P-Node Reporter, which takes these nav star variables, turns them into a message called Node Report that's used by p-Helm IVP, basically aggregates a bunch of individual messages. And then the Helm publishes this desired messages as desired speed, desired heading, desired depth, etc., as well as its state, drive, or park. And so that's what's subscribed to by this translation. And then on the other side, so these desired messages turn into a desired course message in Goby. The node status turns into these nav star variables in Moose. So graphically, that's what we're doing. And in the actual code, you can take a look at it yourself if you're interested, but it's pretty straightforward. And we'll get into some code for these threads in a bit, so it won't be totally a mystery. So how do we run this thread? So we've got this front seat translation, but we need to run it somewhere, and that's the purpose of the Goby, wherever you are, terminal windows. Okay, so we have Goby Moose Gateway is another one of the applications that we looked at the first day, and this one, like the front seat interface, can't do anything on its own. So it needs at least one plugin library to do something. And the plugins in this case are these translation threads. And so, for example, you might end up the plugins could be something like this, where I define Goby Moose Gateway plugins are some shared library. This happens to be one of the ones for the LAMS project at MIT. And then this Corner plugin is another one for use with Goby Corner and Moose. And then once I give it the various plugins I want and delimited by colons or semicolons, I can call Goby Moose Gateway. And then it does something useful for me. So this front seat translation is generally useful because every time we want to run Goby with Moose, we're going to run it. So we can also just do away with Goby Moose Gateway and run it directly in Goby front seat interface. So, so this scenario looks like we can just run the front seat translation directly in Goby front seat interface. And the reason to do this is really just to simplify the number of processes we have to run. It would work perfectly fine if we ran it over here in Goby Moose Gateway as well. Just since it's common and we can just run it straight in the interface. So that looks like, so modify that diagram. Now we've done away with the Goby Moose Gateway. We're just running the Goby front seat interface with the same front seat translation thread, the same interface base that we looked at earlier, some implementation for a particular vehicle. Over here on the Moose side, we still got P-Node Reporter and the Helm. So all the messages being passed around are the same. We just move the front seat translation from Goby Moose Gateway into the Goby front seat interface. Okay. So yesterday's homework had you developing this command message, and had you develop a command message that we sent from the top side to the USB. Actually, this is a pretty good time to take a break. So before we dig too deep into uh, this command structure and getting it to actually modify the vehicle, I'll say let's take a 5-minute break and we'll resume at about 10 o'clock on the hour. So again, if you have any questions, please feel free to post them in Slack. I'll take a look at those. I'll probably be able to answer them at the end of the lecture. Have you asked them like we did in the first day, because this one shouldn't run long. So anyways, see you in a few minutes, and ask your questions. All right, welcome back, everyone. Okay, so as I was just getting into before we took a break here, is we're going to look now at taking the command message that you did in the homework or that I did in my solutions to the homework, and actually bring that all the way through to commanding phelm IVP. So let's first take a look at the command message that I designed, and yours may look slightly different depending on how you interpreted my instructions, which is fine. So if we go into src lib messages, I called mine command underscore DCCL, and if we open that up, I called my message USV command. We got some DCCL metadata. I have a timestamp, and I have a desired state I want my autonomy system to be in. I can either do this waypoints mission, or I can do the polygon mission. And then if I'm in the polygon mission, I can set the polygon sides, so the shape of the polygon, and then the radius in meters. So given that command message, I've subscribed to it from the top side in the USB manager. So in src bin, we got the manager, USB. If I look at the app.cpp for that, I've added this subscribe commands method. And within inside of subscribe commands, at the moment, all I do when I receive a command is write a debug sentence to the screen, to glog. And I've set up my subscriber configuration to add the publisher, the potential publisher of the top side. And I want acknowledgements for my commands. Not surprisingly, I want to know on the top side whether I've gotten a command, and it will retry automatically until it receives it. And I'm only keeping the latest command, and that's to simplify things here. In a real system, you may actually want this queue to be larger, but then you have to manage commands that overwrite each other. So setting one command keeps it simple. If I send a new one, it just writes out the old one. We're good. So then here's our actually subscribe to this group I created, USV command, to the message, USV command. And when I get one, I call on command, which, as I said, just writes the glog right now. So we'll run this. I'll go back here. Let's bring down the trail mission for now. First, I want to edit the, if I go into the launch trail mission, I'm going to add to my USV launch file verbose output to the USV manager so that I can see what it's telling me. And I'll also use the ncurses GUI as well, why not? And so then if I actually go and run this code, I can launch this. So I already configured this to have 0 AVs and 1 1 warp 1. I'll just run it again just to be sure. And then I can do launch those. And my USV is going here at its very slow real speed. And I can look at, if I reattach the screen for the USV Goby3 course, the USV manager, I get this ncurses GUI showing my various feeds. So I split the AV navigation messages, which are none because we're not running any AVs right now. The USV nav, so this is coming over now from the front seat interface. So if you look back at the code now, you know where this is coming from. And then the commands sub window here. So if I open up liaison on the top side, so that's 50,000 port is the topside liaison. I can select my command message, which was the bonus task in the homework, is to load it into liaison. I can then pick my message. I don't know, I'll send polygon, 6 sides, 100-meter radius. So if I click send on this, after a little bit of time, I'll get an acknowledgement. So there's the acknowledgement. And over here in my USV manager screen, I see that I've received this command. And so that's basically where you would been, you completed that assignment. We could now proceed in a few different ways. So we need to get this command over to the Moose side of things. So the command now is essentially in our USV manager, which is connected to Goby3, but it's not anywhere over here in Moose. So we could either move our subscription out of the USV manager and into some plugin, which we could run either in Goby Moose Gateway or within any other of our applications. We could also run, so we could also create a new translation thread, so analogous to the front seat translation, and run that somewhere, which is what we're going to do. So we'll create a new Goby Moose translator subclass, and we'll call this one the command translation. Since we're translating our commands over to Moose, and then once we're gonna look into creating that in a minute to figure out where we want to run it. But we'll run this in Goby Moose Gateway, since that's kind of the easiest place to run it. If you don't have another place you want to run that thread. So if we choose that, we basically end up with that's the diagram that we're going to create. So on the top side, we're running Goby liaison, which is what I just used over here. Then that sends the USV command over to the USV manager, which is what we're looking at over here. And then what we're going to do is republish that command on interprocess, picked up by this new command translation thread we're going to write, run it in Goby Moose Gateway, convert that message over to Moose, and publish it on the Moose side using cmoose conf client as a deploy state message in Moose and a polygon updates message in Moose. And deploy state will contain whether we want to do polygon versus the waypoints, and the polygon updates will include the information about the number of sides and the radius. So the first thing to do this is then we need to republish the USV command out of the USV manager so that it can be picked up by our new command translation. So if I go to the USV manager's app.cpp, inside of this on command callback lambda, I can republish this USV command. And I'll just reuse the same group, because why not? And that group is fully qualified, the full namespace. And in order to call interprocess, I need to capture this class in the lambda. Okay, so now that we've done that, we're kind of down here in our little diagram. So we need to create a plugin library that this command translation can be in. We actually already have one in this course, and this is an SRC lib Moose Gateway, a Goby3 course gateway plugin. We have one because it's in use by the AUVs, and this is used by the AUVs to publish the USV nav as a node report message for the Helm, which then trails the USV. So we're going to augment the existing code here to add our new translation thread. And we'll do that by opening the header here first. And here you can see this IVP Helm translation. That's the one that subscribes to the USV nav and publishes it over to Moose. So we'll create a new one. And I should mention, you could very reasonably add it to this one. I'm just adding a second thread here just to make it clear the full process. So this command translation class is, as I mentioned earlier, a subclass of Goby3 translator. And this particular Goby3 translator uses a particular configuration object, which is Goby apps moose protobuf Goby3 gateway config. And I need to be able to take that in. If you recall, all the Goby threads take a particular type of configuration. In this case, where you're choosing this this message, which is dictated by the choice of the translator itself uses this configuration object, which contains things like where moose is and whatnot. Okay, so then in the CPP, we need to implement this constructor. And while we're running by here, we see these two load and unload functions are used by Goby3 gateway to load and unload our threads. So we need to add our new command translation thread. We need to launch that, and if this were to be closed early, we want to join it. So the symmetry here is good. So let's implement our constructor here. So we had our Goby3 course moose command translation constructor, just command translation, and that's got, as I mentioned a minute ago, this Goby3 gateway configuration, and that we pass that configuration to our base class. We could augment this with additional data that we needed for a particular application, but we're not really configuring our translation thread at all otherwise. So we can just pass it to the base class and let it use it and move on with our lives. So I have a couple of type defs here just to keep things short and clean. Our USB command message, which we need to include the header for. Let's put that up here. So that's in messages command DCCL. tv.h is the generated code. And then we can create our callback here. So we're going to subscribe to this USB command message here. So we'll create a callback called on USB command. And this callback is going to accept a USB command message. Let's call it command. And what do we want to do when we get that command? So this command has it has the desired state field, and we want to publish that as deploy state. So we'll do moose.coms gives us access to the cmoose com client, which is what we can publish on moose. Notify is what moose, that's what moose means. That's the moose word for publish, basically. So deploy state is the name of the variable I want to publish. And I'm going to publish the string version of this enumeration, the state enumeration. So to get that with protobuf, I can always call the name of the enum underscore name. So this function converts the enum to a string, and then it passes the actual enumeration value. So what there is, this whole thing is going to be the string version of desired state, because Moose is all about strings all the time. So the other thing I want to send is if it's the polygon state. It doesn't really matter what order I publish these in, but I'm going to publish this first. Actually, it does matter because I have to update the variables before I change the state in Moose. Forget that. The IVP home requires that. So if it's a Polygon message state that we want to be in, we'll also create the string to update the parameters. So I'll use a string stream for this. Call it update string stream. And then this is the syntax for IVP Helm updating the loiter behavior that we'll add in a minute. So set those to some 0 values so they won't be used. Change the radius to the radius in our command message, and the number of points and the number of sides to our polygon will be the same. So it should be command dot polygon sides. And then finally, we can publish that as well. Notify, again, that's publish and moves. And this is polygon updates. So now we're publishing both deploy state and polygon updates if we want it to be polygon mode. So let's go build that while we move on here, make sure we got everything right. So Helm IVP is a whole nother project with its whole nother set of learnings, but that's not the purpose of this course. It is well documented, however. So if I go to the documentation for it, there's all these behaviors that exist in the open source project that you can use. In this class, I'm using the trail behavior for the AUVs to trail. I'm using the waypoint behavior to do the Goby fish waypoint. And so what we're going to do is we're going to take advantage of the loiter behavior, which is where vehicle transiting and repeating a set of waypoints following a convex polygon. So that's going to be used for our polygon deploy state. So in order to inform the Helm of that, the Helm has a so in launch, trail, config, templates. Helm takes a behavior file. So this usv.bhv.in gets preprocessed into the Helm behavior file. So I'll look at that file here. And for those of you who are familiar using Moose IVP, you'll be familiar with this. You have some initialized Moose variables that we start on startup, and then a bunch of behaviors. In this case, one behavior. This is the Goby fish waypoint behavior. So we're going to change this around a little bit. We're going to change deploy to become deploy state. And we'll have our vehicle start up doing a hexagon rather than the Goby fish waypoints. And when we do that, we also need to change the condition on the waypoint behavior now to be when the deploy state is waypoints. And this maps to the enumeration name of our desired state here, waypoints. And then we'll add a new behavior. And let's copy that in, I'll explain it. So this behavior is, we're going to run a BHV loiter, which is this behavior that is in the open source distribution of IVP Helm. And I'll call it Polygon for lack of another imaginative name. The relative weighting, which doesn't matter because we're not running multiple behaviors at once right now. The condition, which is going to be deploy state as Polygon, that's being published by our translator thread. It updates, which is how you set changes to the behavior on the Polygon updates variable, which is we're also publishing. So that's how we're modifying this behavior at runtime. We'll set center activate, which just means to do the loiter around where the vehicle currently is at a speed of 1.5 meters per second. And then the initial polygon, so until we send in an updates, will be this 0, 0 centered 200 meter radius hexagon. So now that I've changed that and save it, we need to also add Goby Moose Gateway to the launch. We added a new loiter behavior to usv.bhv.in. We wrote the new translator thread. And so then the last thing is to, well, essentially run our new translator thread. And that'll be within within Goby Moose Gateway. So where we do that is first we'll add running it to so launch trail the usv.launch. Open that up, and we'll add in a line for running Goby Moose Gateway. And this is a bit of a mouthful, so we'll work our way through it. So we need to, in order to run Goby Moose Gateway, as I showed you before, it needs to have a Goby Moose Gateway plugins environmental variable, which points to our shared library, libgoby3 course Moose Gateway plugin. So that's built into build libgoby course Moose Gateway plugin, and that includes the code that we just added here for command translation. And the shared library loader needs to know where that is. And since this isn't Goby3 course build lib is not in like USR lib or some common location that's already in the DL open path, we add it to LD library path here. So we add this directory to there. And then finally, we actually run Goby Moose Gateway with the config from the config generator. And I'll finally add double V for debug one verbosity so we can see what's going on. We need to generate this config. So we need to edit usv.pv.cfg.py to generate this. So that's in Goby3 course launch trail config right here. So code usv.pv.cfg.py. So if you've been working on the homework, you've gotten familiar with this preprocessor that's written in Python. There's this big block here that we can do all the apps that it can preprocess, and we'll add a new block here for our Goby Moose Gateway. And that's just doesn't really matter where we add it in here. So we're adding a configuration block for Goby Moose Gateway, which pre-configures this existing template file with the various parameters. And here's where we pass in the correct MooseDB port to that. Okay, so now that we've got that all working, I'm assuming I got this all right, we can rerun the top side and the USV and give it a whirl. Okay, so as you can see, the change I made to the behavior file means that it's going to start on this polygon pattern now, this hexagon centered around the origin of 0, 0. And put that aside there. If I go back over to liaison, and now let's see what happens when I send a waypoints command, which while we're doing that, we might as well also take a look at you there, stay, and then over here we can take a look at the screen for USB Goby Moose Gateway. And now we'll send this waypoints command over to the vehicle. Got acknowledged, but our vehicle still not doing its thing. So here's where we need to figure out what went wrong. So we can take a look at UMS, which is the Moose scope, to see what's been published into Moose on the USV side. So we're expecting a deploy state. This should have changed to waypoints. So something in our new thread isn't actually running. So the first thing I'll do is to make sure I actually built that. And did I save it? Command translation, make sure that's saved, make sure that's loaded, loaded there. And then my launch file for the USV, it's running it. the correct plugin, but it's not actually running. And let's try that again. What points? That's curious. All right. What do we got wrong here? All right, so let's look at the configuration generation here, make sure that looks right. Take it from there. Also make sure we don't have any extra screens kicking around. No, that looks fine. Let's look at what we get here if we run the USV config. Connecting to the right hostdb. Works all right. Things like that. Okay. Got that right. That's saved. All right, place. Let's try to make clean on that. Why not? All right, so just going to move on for now. Come back in this and see if we can get this working afterwards. So the one thing I wanted to get through yesterday that I didn't have time to, so I moved it to today's lecture, is time handling in Goby. So sort of take a trip back in time to that today, if you will. So let's close these out. So if we switch back to the health status message that we were looking at yesterday, which is in src lib messages and health status.proto. Let's open this one up. When we left this yesterday, we only had the state field of this message. And let me just take this out for a second. So this is, a good way. Another thing we may want to do to improve this message is to add a timestamp to it. And this gives us a good chance to look at how time is handled in Goby as well. So in C++ 11 and newer, we have the standard chrono library. But unfortunately, there's no date handling in standard chrono until C++ 20. And we're targeting C++ 14 in Goby. So that's kind of a compromise between the latest and greatest and what people actually have on compilers. And so standard chrono provides some amount of what we need, but not all of it. So we need date, points in time and durations, but we also need a date representation, and we need a serializable representation, some way to send time through our protobuf messages. So the first of these is a point in time. So for example, right now, or a duration, which could be something like 2 hours, 5 minutes. And for these kinds of things, we'll basically directly use standard chrono because it provides that. And the second option is a date representation, the second thing that we're going to want. And since this doesn't, as I said, come into C++ until it's 20, we'll use the existing boost library for this now, which is in POSIX time, p-time. And the third thing we need is a serializable representation. And we have two things we want to be able to send, the point in time or duration. And so for points in time, we'll use seconds represented as a double for microseconds as a int64 type, either signed or unsigned. And this is assumed to be since the Unix epoch, and that's 1st of January 1970, midnight UTC. And to do this, we're going to use boost Unix quantity of time of some kind of time dimension. So in Goby, I type that to Goby time micro time. And this is for the int64 microseconds version. And it's type def to Goby time, SI time for the double seconds version. So you can use either one, and because we're using boost units quantity, you can convert between them without accidentally messing up. So then for durations, we'll also use seconds or microseconds. In 64s, and the same exact type defs, the Goby time, micro time, or the SI time, depending on whether you want to do seconds or microseconds. So all of these representations, the standard chrono-based stuff, the POSIX time, boost stuff, and the micro time, SI time, can be converted. All the conversions can be done with the Goby time convert family of functions for time points, and the Goby time convert duration for durations. And the reason there's separate functions is because you may have noticed that there's no difference in the serializable representation as there is for points in time and durations. They're all just microseconds or seconds. There's just an assumed epoch in the case of the points in time. So you have to use convert for when you mean it to be from the epoch, and duration for when you don't. And that's usually pretty obvious from the message field name. So something like a message timestamp, this you can assume is a time point. And something like, I don't know, deploy duration, assume as a duration. So this is up to the writer of the protobuf message to either choose a good name or make it clear in some other fashion through documentation or whatever you've got. So since the DCCL library has integration with boost units, it's an easy way to set the fields using the with units methods that it adds. We used it a bit yesterday during the inter-vehicle section, but we'll look again now at the units part. So let's add a timestamp to this message. And we'll do that by, in this case, I have a slight preference for the microsecond version. So we'll call this uint64 timestamp field 2, and we can add DCCL field units. So this is micro, and then dimensions of time, which in the SI system is seconds. So this reads as microseconds effectively. So without going into a lot of detail, we can look at, you can go to libdccl.org if you want to read more about this. This will generate the accessors and getters, or accessors and mutators for the with units version of this that uses boost units. So now if we go back to the, we can bulb that, see what I missed, semicolon. So if we go back to the app.cpp for the interprocess one that we were looking at yesterday, which is going to be in src bin interprocess one for the publisher. we can look at that app.cpp, and this wasn't here yesterday. So we now want to set the second field, the timestamp field. So I'll do this out in long form first, and then we'll shorten it up. So we can get the current time. So as a system clock time point, now we can get that from calling Goby time system clock now. And you could use auto here. I'm just making it explicit. So then you can also convert that to microseconds since Unix, and this is something we can then serialize in our messages. We can convert the time we have to a Goby time microtime. So this microsecond representation for serializable representation. So we can convert the now variable to a microtime. And then that's something we can set in our DCCL message. So health status message, set time stamped with units to the now microseconds since Unix. Okay, so this is kind of a lot of code to set the current time. So there's a little bit we can shorten this up with. First of all, I should mention system clock is a very thin wrapper around standard chrono system clock. So it uses the same duration types, period, representations, time points. The only difference is that it supports this warping functionality where you can call time at faster than real time, which is really useful for the simulations. So since you can convert between the Goby system clock and the regular standard chrono system clocks, I would recommend using the Goby system clock everywhere you can, so you can use the warp functionality, but you don't have to. The other thing that's in the Goby version is this overload for now that takes a template parameter of time type, and anything that's supported in the convert family of functions can be passed to this template parameter for now. So that allows us to shorten this up quite a bit by instead we can just directly write health status message, set timestamp with units to Goby time system clock now converted to Goby time microtime, which is the serializable representation that we need. So I can do that and then just delete all that. And this is the short form that I generally use for setting a timestamp to the current time, current system clock time. All right, so on the subscriber side, we might want to do something with this timestamp. So if I open up the subscriber code from yesterday in the interprocess 1 subscriber, and here's where we subscribed to the to our health status message. And here's what it looked like yesterday. And so say we want to get the date out of this timestamp, we can call convert on to a boost units POSIX time, not boost units, boost POSIX time, p time on the health status message timestamp. And then we can do something with that, which the something we'll do with it is just going to be to write it out to the screen and do glog boost timestamp as a date. And then there's a function in boost POSIX time that converts a p time to a string. But if you wanted to know that the day or something like that, you now could do timestamp dot date dot day or something. So this p time object, which is what this is, has all the accessors for days and months and years and all that stuff that you'd want out of a date. So the other thing that we can do is perhaps we want to know, say, the latency between when the message was serialized, that timestamp, and the current timestamp. So we could get the approximate latency as standard chrono microseconds, which is going to be the current time, so Goby time system clock now, minus the time in a message, which we need to convert to a system clock representation in order to subtract them. And then the actual time in the message. So then now that we've got this latency, we can also write that out. Okay, if we rebuild that, go back down here and launch our Goby3. Put ourselves somewhere, doesn't really matter where. We go back to the code here, make sure that actually builds correctly. And we'll run this. The publisher is now, you can see the timestamp. So this is microseconds since Unix in the current time. And then on the receive side, you'll see the timestamp. It's just a message in microseconds since Unix. So the serializable version, the timestamp is a date. So that's today at the current time, UTC. And then approximate latency, which is going to include everything that's going on between the call to now until the call to the stream, the glog output stream. So, given that, you should have a pretty good handle on how the time handling works in Goby. So now we've gone through that, let's see if we can get back and get this moose command example working one more time. And if not, I'll figure out what went wrong, and I'll let you guys know, and we can look at it in office hours if necessary. So let's take one last look through each of those pieces of code. So we've got publishing our USB command message. So let's make sure that we've got that. So if we turn off the auto scroller, we go back up here and make sure that on our Goby3 course USB manager, we've got source, bin, manager, USB. Open up that. And okay, now when we receive our command message, we're republishing it on USB command, the message. So that looks fine. So then we go back to our plugin library. And we go to lib moose gateway. Take a look at the header for this. We've got our new command translation translator, our constructor there. And if we go to the CPP file, we're actually launching that thread when we load this plugin. And then down on oh, there it is. So I wrote the callback, but I forgot to actually subscribe for the message. So if I do Goby, I access the Goby thread, I can subscribe to USB command and call that callback. So I was missing this little link right there. So if we rebuild this, And we'll go back to the terminal windows here and run the all.launch for the USV in the top side. We got our USV starting on its polygon mission. Get this back here. And we'll go to liaison and we'll send, come on, liaison. I'm running still something in one of these windows. So make sure that's going. All right. Liaison. Top side's not running for some reason, so let's check out what that's going on. Let's run that separately as just topside.launch. Who didn't run? Failed to launch Goby3 course topside manager. Why is that? No response from Goby3. Well, right, because it's not running. So we'll run Goby3 for the top side, and we'll run this. Field timestamp missing min. So I messed up something in my timestamp message. So if we go back into there, in the source lib messages, and we open the health status. So I forgot to add to this timestamp message the codec, so boundings. And the codec we're going to use is this time one. So there's this special codec in Goby that's used, or in DCCL rather. DCCL field codec is DCCL.time too. Let's just check that that's what it actually is. Correct. So it's the health status. Yep. So the codec should be time 2. And what time 2 does is it encodes the current timestamp within using the current day as an epoch. So that assumes that your message is received within 12 hours. So it makes it a lot smaller than sending the whole, say, time since the Unix epoch. Let's try to bring that down. Make sure I've got everything closed here. Make sure that all builds. And then hopefully we'll be ready to rock and roll. So if anyone has any questions on any of this, besides the part that doesn't work, feel free to post them in Slack and I'll answer them in the last few minutes here of this lecture. Okay, so now we're all built. Let's kick off this mission, see if everything's running fine. There we go. So now we're off. So the race is here again. We can now load up liaison and send our waypoints command. And then we get this through, gets acknowledged, and there we go. So now our USV is off to the Goby fish again. And if I were to send the polygon command with, say, make it a pentagon, 200-meter radius, I send that, and then we get our vehicle going on a pentagon pattern. And so that ties together the last piece there, the command message that you sent yesterday, into actually making the vehicle do something differently. And after this lecture, I'll push the code that I've got here to post lecture 3. So if you want to take a look at it again at your leisure and start the homework. So does anyone have any questions here? I don't see anything on Slack. There's few enough on that if anyone has a question, feel free to just unmute yourself and ask it. If you raise your hand, maybe we'll see. So anyone have any questions, comments, concerns? All right, well, I guess not. So I'll be on office hours from 1 to 3 and 7 to 9 again today. I'll be on Slack. So good luck with the homework, and come join me on office hours if you have anything you want to discuss or any questions or concerns. And thanks again to everyone for joining. Thanks again to our sponsors, and I'll hopefully see you all again tomorrow.
Thanks, Toby.
Sure thing.